Hello, welcome back. In this video we will see the response of the overdamped system. Already in the previous video we have seen that if zeta value is more than 1, then it is called as the overdamped system. If zeta is 1, then it is called as the critical damping system, and if zeta is less than 1, it is underdamped system. If zeta is more than 1, then the roots are real and negative. Okay, let us see the response of the overdamped system. Okay, if zeta is more than 1, already we know that the roots s1 and s2 are real but negative values. Here, see here, the general solution x is equal to a1 e raised to minus zeta plus square root of zeta square minus 1 omega nt. Okay, where s1 is minus zeta plus square root of zeta square minus 1 omega. This is s2. Okay, it is derived in the previous video. Okay, you can see here. Okay, s1 is minus zeta omega n. Okay, by this we got s1 equal to omega n into minus zeta plus or minus square root of zeta square minus 1. Okay, the general solution is x is equal to a1 e raised to s1t plus a2 e raised to s2t. Okay, where s1 and s2 values are substituted here, s1 and s2 values. Okay, if zeta is equal to more than 1, then it is overdamped system. For overdamped system, the roots are real and negative. Okay, now to find these two constants, we have assumed the initial conditions. Initial displacement, it is assumed that x0, that is some value, and initial velocity, it is assumed that some velocity. Okay, substituting the initial displacement here, that is x is equal to x0 initial at time t equal to 0. If t equal to 0, then this whole term will be 0, minus zeta plus square root of zeta square minus 1 omega n. That is, when it is multiplied with t, that is 0, then it is 0. E raised to 0 is 1. So we will see only a1 here. So x0 is equal to a1 plus a2. As t is 0 here, 0 multiplied by this whole value, it is 0. E raised to 0 is, again it is 1. So you are left with a1 plus a2. Okay. Substituting t equal to 0, t equal to 0, and x is equal to x0, we have this equation. Similarly, we have assumed one more initial condition, that is initial velocity. Initial velocity is v0 or x0 dot. X0 dot. This dot is nothing but velocity. Okay, at time t equal to 0, at time t equal to 0, this is displacement. Differentiating this displacement, then we will have the velocity. Okay, a1. Okay, what is the differentiation of e raised to x? That is x into e raised to x. So this is the differentiation of the displacement function, displacement equation. Okay, now we have the two equations, that is initial velocity equation and initial displacement equation and initial velocity equation. By these two equations we can determine a1 and a2. Then for one system where natural frequency is 3 and zeta value is 1.2 and initial displacement is 1. For this you can see the response here. It is not periodic here, as it is not periodic here. Okay, because the zeta value is more than 1, that is overdamped system. Okay, if zeta is less than 1, then for the underdamped system you will see the periodic nature. Okay, okay, these two figures are very important. You have to mention these two figures in the exam. Okay, okay, thank you. This is the response of the overdamped system. You must mention these two equations, that is initial displacement equation, initial velocity equation. Then you take an example of natural frequency, zeta value and initial velocity, and you should draw this curve. Okay, for this system, for these values. Okay, this represents a system, a overdamped system. Overdamped system of zeta is more than 1.2 and natural frequency is 3 and initial velocity. Okay, similarly for different zeta values, what is the response of the displacement to initial velocity ratio? Okay, this is very important. In the exam it will be asked to mention the response of the overdamped system. Okay, then you have to explain all these things. Okay, thank you.